And so, to account for different types of non-idealities, folks over the course of history have developed an array of different equations of state. There are two general classes of equations of state I want to talk about. The first class are going to be cubic models, where, I guess you could write them in such a way that on the right-hand side, they would have volume raised to the third power. So like a cubic sort of equation. Though generally we don't really write the equations that way. All right. The first type of van der Waals equation of state, cubic model equation of state I want to talk about, is the van der Waals model. All right. And so this was really historically the first sort of equation of state that was able to account for non-idealities in a gas. Okay. And so previously I introduced to you, that we could describe the multiplicity of a van der Waals gas in a certain way. We had a function for it. If you take that multiplicity and you apply the calculus of thermodynamics, you could show that the pressure, you could relate that multiplicity to pressure, and you would end up with an equation that looks like this. Okay? Where N is moles. But we could also rewrite the equation by dividing out moles on each side. Or we could rewrite the equation like this. Where in the left-hand term, we could divide the numerator and the denominator by n. And so what we would end up with is this, where we have molar volume now. And on the right-hand side, we could just move this thing down here so that we would have A divided by molar volume squared. Okay? All right, and so this is what we call the van der Waals equation of state, where it kind of looks like the ideal gas law, except now we have two terms, and there's also these two constants that we have to deal with in the van der Waals gas, where this B constant accounts for the volume of the molecules, of the gas molecules, and this A term accounts for molecular interactions between the gas molecules. Okay? And so this was the first equation of state. Ideal gas law didn't account for these things. And so the van der Waals equation of state does account for them. Now, some properties of the van der Waals gas I want to point out. If you looked at very large volumes, you would see that at a very large volume, this V would be much greater than B, so the B would kind of go away. And at very large volumes, this denominator term would dominate, and this entire second term would go towards 0. And so at large volumes, what you end up getting is that your pressure essentially simplifies down to this. Right? And so what you get is back is the ideal gas law. Which makes sense because, once again, one of the assumptions for the ideal gas law is that your system volume is infinitely big. Right? So it makes sense that if you go to large volumes, the van der Waals gas turns into the ideal gas law. On the other side of the equation, or on the other end of the spectrum, I should say, if you go to very small volumes, your pressure skyrockets towards infinity. Right? And that's because the system starts approaching the size of the molecules. Right? And so mathematically, you could see that if V is equal to B, in the denominator you would get 0. And 1 over 0 gives you infinity. Okay? Or, a more physical explanation, if the volume of your space is the same size as the molecule, right, it's always going to be bouncing and hitting the walls of your system, right? And so in that case, the pressure, which is just force over area, if that area is very small, then that pressure is going to be very large, infinite. Okay? All right? And so that's the van der Waals gas. And so that was the first one to be sort of developed after the ideal gas law. But it worked well, and it gives us some idea of how molecular interactions and the molecule size impact, let's say, pressure. But it wasn't perfectly accurate. And so over the years, and especially during the 1900s, folks spent more time deriving, more sophisticated equations of state that were more accurate and were better able to account for, molecular interactions, right? And so when I call these kind of generalized cubic model equations of state, essentially they all kind of have this form, where that first term is the same as what we saw for the van der Waals gas, but then the second term is just some function, which I call delta, or triangle, that accounts for, that's a function of both temperature and volume, right? And so delta can have different functional forms. So one example would be an equation where delta has this form. Okay. All right, and so when delta is like this was known as the Redlich-Kwong equation of state. So this was developed in 1949. Okay, and you can see here that it uses the same A parameter that the van der Waals gas has, but now it's dividing it by the square root of temperature. Okay, so that kind of programs the temperature dependence into that second term. You also see that the denominator now also accounts for the size of the molecule as well. Okay. All right, so that was the Redlich-Kwong equation. And so Redlich-Kwong delta has that form. But there's another version of the cubic equation of state where delta has this form. Where this other lowercase, or this theta term, this is also some function of temperature, and a more complicated function of temperature. It's not just like a square root. Okay? In any case, so that's another way of expressing delta. All right, and so this is what Suave did in 1972. This person developed this equation. All right, or, once again, another version of delta was derived that looked like this. All right, and this version of delta was known as the Peng-Robinson equation. And this one was developed in 1976. All right. All right, so there's different forms of the cubic model equation of state, but which one's the best? All right, which one works well? To give you an idea of how well these work, what I want to show you is some actual data. Okay, so I'm showing you a plot from this paper that was presented at an aerospace meeting for carbon dioxide at different temperatures. And for the aerospace industry, this is important because for their space shuttles and stuff, the reactions, they're having a giant combustion reaction in order to, lift off the shuttle. And so they're very concerned about, what happens to carbon dioxide as it goes through various valves, as it changes temperatures, things like that. Okay? And so what we're looking at here is a plot of, on the y-axis, density, which is inversely proportional to the specific volume, versus temperature. Okay? And the black dots here are the density of carbon dioxide at different temperatures. So you see it has kind of this sigmoidal shape like that. And then the solid lines that we see, these are different equations of state that correspond, if you plug in parameters corresponding to carbon dioxide, these are what the predictions for the density or inverse specific volume would be. And we see that if you try to use the ideal gas law to describe the density of carbon dioxide, you could see that you're going to be way off, right? We see that the measured data, especially as you go to low temperature, you see that the measured data are around 1,200 kilograms per meter cubed, but the ideal gas law would give you something around 200, right? So you'd be way underestimating the density there. But I will point out that when you go to high temperature, the data and the ideal gas law begin to agree, right? Because once again, at high temperatures, you start satisfying the ideal gas law assumptions. All right, in any case, but at low temperatures, the ideal gas law is terrible. It doesn't work at all. The green line here is the van der Waals equation of state. You can see it's closer to the data, but it still underestimates it quite a bit. The purple here is the Redlich-Kwong, gets closer to the data. The teal is the Redlich-Kwong, or the SWAV, gets closer to the data. But that Peng-Robinson, describes the data pretty well, at least in the region that the data were collected. Okay? And so you could see, at least for carbon dioxide, I'm not saying this is general for all gases or chemicals, but for carbon dioxide, the Peng-Robinson equation works pretty well for describing the density as a function of temperature. Okay? And so earlier, I point out that as you go to high temperature, all of these models basically collapse into the ideal gas prediction. Right? But what I also want to point out here is that, once again on the y-axis, it's density, or inversely proportional to volume. And so if you go to low density, that's the same thing as going to large volumes, right? And so you could see here that at large volumes, you would get the ideal gas law. But for our real systems, our volumes aren't that large, right? They're, relatively small compared to infinity, right? And so that's, by using these more sophisticated equations of state, that's why we could get more accurate estimates of things like pressure or volume or temperature.